This is AQA A-Level Chemistry, and it is the Equilibria Year 13 topic, where we're going to be looking at KP. It's part 1 of 1. The whole of this topic is included in this video. But I do recommend you go back to look at the videos on KC in Year 12 and the other Equilibria topics, because all of the information in there builds to what we're going to be doing now, and we're going to add some new information for Year 13 content. As always, I'm going to recommend that you pause the video as you go, have a go at the activities, try them for yourselves so you know what you know and you know what you need to work on. So KP, we need to know about partial pressure, we need to start applying equilibrium law to gaseous equilibria, and we can look at predicting the effect of changing pressure and temperature on gaseous equilibrium. To begin with, have a read through this, a very simple task at the bottom. And as I've already touched on, Kp is the pressure constant. Now, you've learnt about Kc, which is the equilibrium constant. That's a constant that we measure where reversible reactions are happening in solution. Kp, the pressure constant, deals with gaseous reactants and products. Now, if we're going to be able to do Kp calculations, we first of all need to be able to calculate partial pressures. So at the bottom here, we've got oxygen with a pressure of 20 kilopascals, nitrogen with a pressure of 40 kilopascals in identical vessels, identical containers. If we move the oxygen and nitrogen together into another identical container, what do we think the total pressure would be? And hopefully you got that it would be 60. You simply add together the partial pressures so you can work out the total pressure. So now let's apply that to this question here. And we're using something that's quite familiar to us. We've simplified the composition of the air. We're saying that it's 80% nitrogen and 20% oxygen, and we know the standard atmospheric pressure is 100 kilopascals. So what would be the partial pressure, the pressure exerted by each of the two individual gases? Well, we've got the percentages. 80% is nitrogen, 20% is oxygen, so it stands to reason that nitrogen will contribute 80% of the total pressure and oxygen 20% of the total pressure, giving us 80 kilopascals and 20 kilopascals. So far, so simple, but we're going to use this and build on it to get to the more complex calculations that you will be facing. These two equations are incredibly important for your calculations. You need to be able to work out the mole fraction of a gas, and that's simply the number of moles of that gas in a mixture divided by the total number of moles of gas in the mixture. So, for example, if I had 100 moles of air and 80 of those were nitrogen, it would be 80 divided by 100, and I would have a mole fraction of 0.8. Now, from there, we've got the partial pressure, which is the mole fraction. We've just calculated that for nitrogen, 0.8, and we're multiplying it by the total pressure. That's standard pressure, 100 kilopascals, and those two steps take us to the 80 kilopascals pressure that we saw on here. Okay, writing expressions for Kp. Now, you've written expressions for Kc, and these are done in a very similar way. I've got one example here that I've laid out, and I'm going to colour code in a second so you can see, and I'm also going to show you an alternative way of doing it. There are certain things that are the same as Kc, but there are things that must be very, very different. One of the things that's the same is that Kp is the product over reactants, and you can see that I've put those in, the Y and the Z, capital Y, capital Z, on the top of the line, and A and B under the line. Also similar to Kc is that when we do the powers, it's based on the balancing of the equation. So Y is to the power Y, uppercase Y to the power lowercase y, Z to Z, B to B, and A to A. But as I say, we're going to look at an alternative method. Have a go at how you would represent these two. Well, in the first instance, Kp, I have got Kp is pressure, and I've done it now with a P and then the substance in brackets. So pressure of HI, and it's squared. It's squared because I've got 2 HI, so it's HI squared. And that's products, and it's over reactants. So I've got P of H2. There's no power because there's no balancing. It's 1. And I2, so I've got P of I2. Again, there is no balancing there. And I've put the state symbols in. This is Kp, the pressure constant, so they are always going to be gases. So let's try the next one. Well, Kp is pressure of NH3, and that's squared because I've got 2 NH3 that you can see here, and I am dividing by H2 cubed because I've got 3 H2, and N2, no power there because it's 1 mole of N2. Once again, I'm adding the state symbols. This is the gas constant, the pressure constant, so they are all G. So what would the units look like for each of them? Well, let's remind you of the expression for Kp here, and let's imagine that we're working with the unit Pascal. So if I do this in long form and I break it down step by step, I have got Pascal squared on the top, and that's divided by Pascal times Pascal. So if I expand that, I get Pascal times Pascal over Pascal times Pascal, and they will all cancel out. It means in this first example, Kp has no units. Now do the same for the next one. So on this one, I've got Pascal squared on the top and Pascal cubed and Pascal on the bottom. Once again, just to illustrate this clearly, I'm going to expand those out. Pascal, Pascal over Pascal, 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 Pascal. And I can get rid of, I can cancel out 2 of the Pascals on the top and 2 of the Pascals on the bottom, leaving me with 1 over Pascal squared, which in standard form I would write as Pascal to the minus 2. Now bear in mind, this is Pascal. It could be in atmospheres. It could be in kilopascals. You must always use the units as appropriate for the question that you are on. So the remainder of this video is going to be working through some increasingly complex Kp calculations. Again, I'm going to remind you, have a go at these and then review your answers. So in this first example, I have been given the partial pressure of A, of B, and of C. I'm going to start by writing out my expression for Kp. So I've got Kp is P to the B, Pc over Pa. That's product over reactants. I've included the state symbols. They're all gases. And I've got the numbers provided. A is 5.1. B and C are both 95. I've colour-coded them so you can see precisely where they are coming from. And once you've done that, you can carry out the calculation and it will come to 1769 kilopascal. And it's kilopascal because my units would be kilopascal times kilopascal over kilopascal. I can cancel out the ones I've shown here. I'm left with kilopascal. For the next question, see what you can do. Now, once again, I'm going to start with my expression for Kp. P is NO2 squared over N2O4. But I can't put all of the figures in straight away. We do know that NO2 has a mole fraction of 0.8 and the equilibrium total pressure was 123 kilopascals. So I'm going to need to use my partial pressure calculation, and that gives me a partial pressure of 98.4 kilopascals. Now I know that, I can work out the partial pressure of my dinitrogen tetroxide, my N2O4, which is the remainder of the 123. Alternatively, you could have worked out that the mole fraction is 0.2 and multiplied by 123, and that would also take you to 24.6 kilopascals. I can now substitute those figures into my Kp expression. I've got my 98.4 and that's squared, and I'm dividing by 24.6. That takes me to an answer of 393.6 kilopascals. And once again, I've shown how we're working out the units for Kp down below. More complicated question now. See what you can do. So in this one, we've been given percentages, but they are essentially mole fractions. We've also got the total pressure, which is 79 atmospheres. So knowing both of those, we can work out the partial pressures. Partial pressure is total pressure multiplied by mole fraction. So for N2, 79 times 21 over 100. For H2, 79 times 63 over 100. And NH3, 79 times 16 over 100. I carry out those calculations and I get my partial pressures. 16.59, 49.77 and 12.64. And give or take a tiny bit of rounding, what you should find is that they add up to the total pressure. That's a quick check if you're going through and checking your calculations. Now I've got all of those. I'm going to write my expression for Kp. And I've got my expression for Kp and I have my partial pressures, so I substitute those in with colour coding to help you. Once I've done that, it's simply submitting all of the numbers into the calculator, giving me a value of 7.81 by 10 to the minus 5, this time kilopascal to the minus 2. Again, so we can see the working, I've got kilopascal squared on the top and kilopascal cubed on the bottom. I cancel out the kilopascals I can, and I'm left with 1 over kilopascal squared, kPa to the minus 2. Have a look at this one. So this is the same question as last time, but there is one fundamental difference. There is an extra layer of complexity that you would need to consider. We know that 16% is NH3, and therefore we know that 84% is left, and that's going to be our combination of N2 and H2. We also know that N2 and H2 were added in a 1:3 ratio, and they are used in a 1:3 ratio. So whatever is left will be in a 1:3 ratio. So what we really want to do is find out what a quarter of 84 is. That's 21. Just spotted an error here. That should be 63% for 3 times 21. The 21 to 63 gives you your 1:3 ratio. At that point, you can proceed with the question exactly as you did before. You've got your mole fractions. Next question for you to try. So on this one, partial pressures, we were told 50 kilopascal hydrogen, 50 kilopascal iodine, but we're also told the total pressure was 350 kilopascals. That means we can work out what HI is. It's the remainder. So 350, take away the two 50s, and that gives us 250 kilopascals. I'm then going to write my expression for Kp. I've got my P, HI squared over pH2 and PI2. And I can substitute my figures in directly. Look at the colour coding so you can see where they have come from. When I carry out that calculation, I get a Kp value of 25. There are no units, and here is why. Kilopascal squared over kilopascal squared, they all cancel out. Okay, a more complicated question again. So in case C, you might remember doing tables and calculations whereby you know the initial moles of some and you know the equilibrium moles of others, and you've got to work out the equilibrium moles of all of them. So this is one step before working out the mole fractions. I'm going to draw out my table, and the table is each component of the equation, PCl5, PCl3 and Cl2, and I've got initial moles and equilibrium moles, and let's fill in what we know. Well, we know we started with 1 mole of PCl5. We also know we started with no PCl3 and no Cl2. We have also been told, however, that we've got 0.816 moles of Cl2 at equilibrium. We now need to do some calculations to work out the others, and we're going to use the balancing of the equation to help us. Because we know in the equation that for every mole of Cl2 that's made, there's 1 mole of PCl3 made as well. It's a 1-to-1 ratio. So my equilibrium moles of PCl3 must also be 0.816. What we then need to do is look at the mole ratio between PCl5 and one of the products. So 1 mole of PCl5 makes 1 mole of PCl3. Therefore, to make 0.816 moles of PCl3, I would have used 0.816 moles of PCl5. So my equilibrium moles is what's left. 1 take away 0.816, giving us a value of 0.184. Now I've got my equilibrium moles, I need to work out the mole fraction. So my mole fraction, remember, is the number of moles of the gas that we're investigating divided by the total number of moles. 0.184 plus 0.816 plus 0.816 is 1.816. So we're going to divide each of those equilibrium moles by 1.816. And that gives us an mole fraction of 0.101, 0.449 and 0.449 respectively. And if you want to just clarify you're on the right track, they should add up to 1. Now I've got the mole fractions, I need to work out the partial pressure. I know that my equilibrium pressure, total pressure, is 100 kilopascals. So I'm going to multiply each of my mole fractions by 100. We get 10.1, 44.9 and 44.9. I am now finally at the stage I can write my expression for Kp and I can substitute my figures in. And again, I've used that colour coding to help you see where it's come from. That's going to give me a value of 199.6 kilopascals. And as I've done with all of the previous examples, I'm going to show you that it's kilopascal times kilopascal over kilopascal. We can cancel out the kilopascals I've crossed out there, and that's why the unit of Kp here is kilopascal. On to the next calculation. Similar theme to last time, but slightly more complicated again. So I draw out my table, SO2, O2, SO3. I fill in the initial moles that I know, 2 moles and 1 mole of sulfur dioxide and oxygen respectively. And I also know then that I started with no SO3, so I can put my 0 in there. But I do know that I ended up with 1.96 moles of sulfur trioxide. Now from here I need to work out my equilibrium moles of SO2. Let's deal with the SO2-SO3 mole ratio. First of all, it's 2 to 2. 2 moles of SO2 makes 2 moles of SO3. That means that if I want to make 1.96 moles of SO3, I needed 1.96 moles of SO2. So my equilibrium moles is 2 take away that 1.96 and I get 0.04. The next one is a little bit more complicated. 1 mole of O2 makes 2 moles of SO3. So if I'm making 1.96 moles of SO3, I'm going to need half as many moles of O2. Now that's 1.96 over 2, so I do 1 take away 1.96 over 2, which is 0.98. That leaves me with the 0.02 moles of O2. We can see here the equilibrium sits a long way to the right hand side. We've got a huge amount of the product. Now let's move on, because once I've got my equilibrium moles, I can calculate my mole fractions. My mole fractions, well, my total number of moles here is 2.02, 1.96 plus 0.02 plus 0.04. So I can divide each of those by 2.02 and I get my mole fractions, 0.02, 0.01 and 0.97. Again, a quick check here, they should all add up to 1, and they do. Now I can work out my partial pressures. I've got my total pressure, 7.84, so I multiply each of my mole fractions by 7.84, and that will give me partial pressures 0.1568, 0.0748 and 7.609. And again, if you want to do a quick check here, if you're clarifying you're on the right track and you've got time to review your answers, they will add up to, within a rounding, 7.84 atmospheres. Now I can find my expression for Kp, P SO3 squared over P SO2 squared times P O2. And I can substitute my figures in. And that will give me a value of 31,482 ATM to the minus 1. And again, I'm going to show you how the ATM to the minus 1 has worked out. Now look at the size of that. It's a huge, huge number. And that fits with the idea that the equilibrium shifts far to the right. The further to the right your equilibrium is, the larger the KP value will be. Next question for you to try. So once again, we need to work out our equilibrium moles. Here's my table. And we are told that we're starting with 0.2 moles of N2O4, so 0 NO2. There's another little calculation thrown in here, just to add complexity to the question. We don't know how many equilibrium moles of NO2 there are, but we know there were 4.6 grams. So we can do N is M over MR, and we get 0.01 moles. That can go into my table. And from there, we know 1 mole of N2O4 makes 2 moles of NO2. So to make 0.01 moles of NO2, I would need 0.005 moles of N2O4. So 0.2 take away 0.01 over 2 gives us 0.195 moles. Now from there, I can work out my mole fraction. My mole fraction, in each case, I'm dividing by 0.205, the sum of the total number of equilibrium moles. And that gives me mole fractions of 0.95 and 0.05. They add up to 1. Quick check, I'm on the right track. And then I need to work out my partial pressures. I am going to multiply both of them by the total pressure, 0.431 atmospheres, giving me 0.410 and 0.021. Again, a quick check. They add up to the total pressure, 0.431 moles. So finally, I write my expression for Kp. I substitute my figures in, and I get my value of 0.001 ATM to the minus 1. Again, let's take a look at that. At equilibrium, we have got a huge amount of reactant and a very small amount of NO2. So it makes sense that the Kp value will be very low because equilibrium lies to the left. That takes us to the end of this video and the end of this topic. Thank you for listening, and goodbye.